So in this series, I want to chronicle the development of a game that is a Tetris clone. You know Tetris, where you have the little blocks made of 4 squares. I'm doing a terrible job drawing one now, but you have the blocks made of 4 squares that fall down into the playing field, and you have to arrange them so that you have an entire line of blocks that can then get cleared out as soon as you have an entire row of blocks there. The difference I want to make is, in normal Tetris, these blocks fall at a steady rate, right? They've got a steady velocity falling down. What I'd like to do is simulate a couple different things. First, I'd like to change this steady rate falling down into an actual acceleration to mimic free fall acceleration due to gravity, where the block is falling faster down below than it is up above when it starts out. But I also want to add in the drag force that acts on these things. So as this thing is falling down, it's going to pick up speed. That also means it's going to pick up some air resistance that counters this downward force of gravity. And so you actually end up with a steady speed toward the bottom, but you have it speeding up toward a terminal speed here. And I think you could use that strategically, for example, because one of the factors in drag is how much surface area the shape encounters. So for example, this shape would have a surface area facing the wind of 1, 2, 3 squares. This square doesn't count because it's not facing into the wind like that. But if I were to take this shape and rotate it sideways like this, then it would have 1, 2 squares going into the wind, because as the wind comes up and hits this, it has to go around this square and go around this square, but these two are no longer facing in the wind. Or as another extreme example, the ever popular vertical bar that's made of 4 squares going vertically would only have 1 square going into the wind, so this shape would be rather aerodynamic. But if you rotate it, it would have 4 squares going into the wind. 1, 2, 3, 4. This would be rather not aerodynamic. So this long piece would fall very slowly when rotated this way, but it would fall faster rotated this way because of that difference in the magnitude of the drag force that it meets. And so that's what I've got started here in this code, is the basics of a Tetris game. Here I've created the keyboard controls where the right key will move the piece to the right. Here the left key will move the piece to the left. I've also mapped that onto D and A because apparently W, A, S, and D are popular directional controls in addition to the arrow keys. And then we'll use the up or the W keys to rotate the piece. I don't have rotation implemented yet, so this line is just a placeholder. I've even got a note to myself that this line is just a placeholder. Basically, this is the way you set up these key controls in VPython. You just use this scene.bind command so that every time a key is pressed, it'll go to this key input function. Then we need to create a list of the squares that are at the bottom. Remember, we have these, once these pieces reach the bottom, they need to get frozen in place so that you have these blocks as part of the landscape. So this will be our list of squares that have been frozen in place. And then we have the boundaries for the playing field. So we've got a bottom edge, a top edge, left edge, a right edge. And we'll create a little box around that. So we've got 4 boxes here to make the 4 walls of the playing field. Currently, I have just a skeleton outline of the code. We'll develop this over the course of the series. But right now, to create the active piece, I've just made that a box just to make sure that everything works. So let's press Control 2 to run this. So here I've got my active piece. Again, it's just a single block in this playing field. And so I'm going to test this. Again, you can't see my keyboard, but I'll test this with my left and right arrow keys. There's the right arrow key. Here's the left arrow key. Good. Here's the D key. And here's the A key. And again, there's nothing worth rotating right now for the block. But you notice I can keep moving this to the right or the left as much as I want. It'll leave the playing field. So one of the things we'll do today is keep the piece from leaving the playing field. Going back over to the code, just the way this will end up working, we'll have a main loop where we generate the next active piece. Then we'll have the actual animation loop where the active piece will begin to fall. So that's where we'll be updating the active piece position. And then we'll check for whether the active piece needs to be added to the list of frozen squares. If it has been added, then we need to go to the top of the main loop. And we're first going to check for whether a row is full of frozen squares, and if so, then we get to clear it and move the rest down. Do I need to make a reminder to myself for that? And move the rest down. There we go. I suppose that's a much harder version of Tetris, is if the pieces don't move down after you clear a row. And so what I envision for this, we'll start out with the basic Tetris animation of the block kind of making its way down at a steady pace. Then we'll add the acceleration. Then we'll add the drag force. And if you have other suggestions for aerodynamic forces to include, I can include those as well. I don't know any others that are relevant to this scenario, but we can also add other forces that are of interest. And then basically we can play around with the play controls and maybe give the player options for increasing or decreasing the drag coefficient, for increasing or decreasing the mass of the blocks, things like that. Maybe as you level up, you can make adjustments to the game like that. But for right now, let's work on making sure our active piece can stay within the boundaries of our region. So let's think about this. I want to check for whether, let's go over to the right edge first. I want to check for whether the right edge of my block overlaps with the left edge of the right wall of the playing field. That's a lot of words to say. I want this check for whether this piece is lined up with this piece over here. So let's see how we might do that. So let's check on this here. So we only want to move this if it can be moved to the right. So we want to think about if the active underscore piece dot position dot x. So that's giving me the position, the location of the center of this block here. I want to go from there over to this side here. So I want to think about that minus, let's see, do we name the right wall? We should probably name these walls, I suppose. Okay, I can just reference field underscore right here. That ought to be fine there, since they're so thin on this side. Minus field underscore right. So we're looking for that distance. So basically, if that is less than or equal to the width of the, or half the width of this active piece, so active piece dot width, and we'll need to figure out a way to define the width in a minute. I need to remind myself whether that's automatically defined for this box. Then we can, actually then we don't want to, so we want this to be if it's greater than or equal to. There we go. All right, let me check really quick for whether this thing has a width. So print active underscore piece dot width. I believe it already has an attribute called width. So let's see what happens there. Yes, it does print a width for me. It's got a width of 1. So I can try moving this. It's not allowing me to. Let's see. Oh, right. Because I actually need to make this the, let's see. Currently this is going to be a negative number. So actually I need to flip this field right to the other side. There we go. Field right minus this. Okay, let's try that now. Okay, good. It's allowing me to move. Now the question is, on this one, is it going to allow me to move? It does not. Okay, cool. I can keep trying to ram against that wall. I'm tapping the right arrow key. It's not letting me get out that way. Okay, so that works. That's pretty great. Excellent. Now let's try doing the same thing with the left edge. So let's copy this part here, paste it here, tab this in. And so now I want to check for this against the field left, but I want to flip this back the other way because I want this to be a positive number since I'm checking for whether it's greater than or equal to something. So let's hit Control 2 there. All right, right should still be working. Yep, that didn't change anything about the right. Let's check this on the left. And it's working on the left. Okay, awesome. So what I'll have to do, because this is obviously not a Tetris block yet. This is just a single square, well, cube, but in Tetris terms, it's a single square. What I'll need to do is figure out a way to assign a width to this piece. So I'll make a note to assign a width to the piece. And that will need to be adjusted when we rotate the piece. So for example, when I have my T-shaped Tetris piece, my personal favorite of the Tetris pieces, here it would have a width of 3. But if I rotate this piece so that it points this way, in that case I have a width of 2. So I'll need to make a note to myself, another note, up here, that when I rotate the piece, I'll need to update the value of width. And of course, that's also going to be important when I calculate the drag force, like we talked about earlier. Okay, so I think that's a pretty good start for now. In the next episode, we'll start working on this animation loop to get our active piece down into the bottom and work on getting it added to our list of frozen squares. Awesome. Thank you so much for watching. I will see you next time. Bye-bye.